So we talk about half-life in terms of how long does it take for half of the radiation rate to get to half. How long does it take for half of the atoms to decay? See, if you start off with something like some pure radioactive substance, sometime later, that substance will all convert to something else. Like all the uranium that exists in the world today will one day be lead. Lead, whether the world survives or not, will all be lead. Now, how long does it take for half that uranium to decay? It turns out a long time. It turns out 4.5 billion years. Yeah. And you know, when I used to prospect for uranium, I used to find uranium. You know, and every time I'd find uranium inside that rock, guess what also was there?
Lead.
Lead. And guess how much lead compared to how much uranium? About same. Which means that what? The age of that rock is about what? 4.5 billion years. That's the age of the Earth. So 4.5 billion years is the radioactive half-life for the isotope uranium-238. That means in 4.5 billion years, all the 238 atoms around, half of them on the average will have decayed to something else. Now that's a long half-life. A shorter half-life is like radium. Radium, I think, is 1,620 years, something like that. And radioactive carbon-14, that's 5,730 years. And little neutrons, it turns out a neutron by itself is radioactive, will decay. And that'll decay in about 12 minutes. Half-life about 12 minutes. And then a little mu mesons that are 2/millionths of a second, half of them will decay. So there's a whole range of radioactive half-lives. And here's the old story. Let's suppose you have a gram of radioactive substance, and it has a half-life of 1 day. Something used maybe in medical research, yeah? 1 day. How much of that gram will be left at the end of 1 day? And still be the kind of substance it is. Begins with a H. Very good. How much will be left at the end of 2 days?
1/4. Quarter.
Right. Don't be wimpish. Come on. Get it out. You are university level, right? 1/4, honey. All right. Now, what would the wimps say? 0. They say 0. Say, well, you lose a half one day, you lose a half the next day, I'll be gone. What do we university types think about that? Needs a little more careful scrutiny, right? Because you could have started off with a half to begin with, right? Okay. It's going to keep going half. It's like the old bit about, do you ever talk about this thing? We're going to jump to the wall, and every time I take a jump, I get halfway to the wall. How many jumps before I hit the wall? And what's the answer?
Never.
You guys heard of that before. You'll never hit the wall. If every time you jump, you get halfway. Let's suppose I want to go from here to here. Whoop, it's a half. Then 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 a half. I never get to the wall. So in a similar sense, with radioactive decay, you never get to a point where there's no more atoms left. In a practical sense, sure you will. But when you're talking about radioactive decay, it's always nice to work with large populations. Hence, half-life is more meaningful in that sense than going for the life of the whole thing. You might have one that, let's suppose you go, and there's one left. And 20 years later, now, does it make sense to say the lifetime of that material is 20 years? No. Take half of that. That time, you got enough large numbers in there that your half-life, your value can have more meaning.